Okay, so welcome to this next video in the Theory of Probability playlist. In this video, what we're going to do is we're going to do a very simple example of calculating conditional expectation. Right, so this is the setup for the problem then. So we have some abstract probability space here, which is going to be mapped onto the real line by a random variable, which remember is a function mapping an abstract probability space onto the real line. So this random variable x is going to map our abstract probability space onto the real numbers. So every outcome in our probability space is going to be ascribed a real number, and the function is going to be onto. So every real number in the entire real line here is going to have some outcome, at least one outcome, mapped onto it. Okay, right, we are going to make the probability space structure on this probability space here mirror the probability space structure on that, so that the two are homomorphic. Okay, right, what we now want to do is we want to discuss what the PDF on this probability space is. Right, so the probability density function, well, the random variable x is going to be normally distributed, and it's going to be standard normally distributed. So the mean is 0 and the variance is 1, basically. So that means that if I want to know the probability density function for the random variable x being at any point, so let's say if we've got a little x here, the probability density function that you are at that little point is going to be 1 over the square root of 2 pi e to the negative x squared over 2. So that's just the PDF of the standard normal distribution. And what this means, remember, is it's not possible anymore to ascribe a probability that you will get the value little x, because the probability that you will actually get the value little x is 0, because there are uncountably infinitely many real numbers, and the probability that you'll get a specific real number in this case is 0. However, what you can ask is a slightly different question. What you can ask is, instead, look at this point, little x here. Draw a little interval here. So a little interval of length delta x. So go from the point x to the point x plus delta x. That will create you an interval of size delta x. So there's our little interval of size delta x here. Right, now instead of asking what is the probability that you actually are at the point little x, instead what you can ask is what is the probability that within a tiny little interval from x to x plus delta x. And basically you can calculate what the probability that you'll be in that interval is. And what you can do is you can take the probability that you're within that interval. So let's take the probability that you're within that interval. So let's say we have found the probability that you're in that little interval. And basically what you can do is you can let delta x get smaller and smaller and smaller. And what's going to happen to the probability that you're within that interval as the interval gets smaller and smaller and smaller? Well, the probability that you're within that interval is also going to shrink. So what you can then do is you can take the, this is going to go to 0 basically, as delta x goes to 0, but what you can do is you can divide it by delta x. So you can take basically, this is what is known as the probability density basically, because if you think about what this is asking, this is saying, look at this interval, x to x plus delta x, find me the probability, and then divide it by the length of the interval. What that effectively does is it finds you how dense is the probability. It's basically saying it's just like if you've got a rod, and that rod has a certain mass basically, and if you want to know what the mass density along that rod is, what you do is you divide it by the length of the rod, and basically then what you get is the mass per unit length, basically. Now, in this case, what we're doing is we're taking the probability and dividing it by the length of the interval. So effectively what we get is the probability per unit length. That's why it's called probability density. Okay, so it's the equivalent of density in mass, where you think of probability here as being the equivalent of mass, and the probability density is the equivalent of the density of mass. So what you can think of is, this is a rod basically, and you've got different amounts of mass at each point basically, but we can take the total mass of the rod and then divide it by the length and get the overall average density across there. Now, as we take delta x smaller and smaller and smaller and smaller, the density doesn't converge on 0. Because this one goes to 0, but at the same time this goes to 0. So basically, they're both falling to 0, so that the rate, they normalize each other out basically, and continue to be a finite value. So you can make delta x smaller and smaller and smaller, and this will still give you a finite value basically. Now, as you get delta x smaller and smaller and smaller and smaller, approximately the probability, probability density is going to even out, because originally the problem is, so let's do it in terms of rods and mass. Basically, if you think about this rod, you could have a really thick bit of the rod here, which has loads of the mass, and then have a thin bit of the rod over here. So the density at different points is different, basically. The amount of mass per unit length is different at each point. So when you look at the whole rod as a total and take its total mass and then divide it by its total length, it's sort of finding you the average density. It's not telling you what the density is here or here. It's telling you if the mass was uniformly distributed along this rod, what would the density everywhere be? Similarly, this gives you, if the probability was uniformly distributed over this little interval, what would the probability density be? But as you make the length smaller and smaller and smaller, then the variability in the distribution of mass gets trivial, basically. So as you get smaller and smaller and smaller, this the density, the probability density gets more uniform, basically. Every point in that rod is approximately going to have the same probability density as you get it smaller and smaller and smaller. So this actually converges on a value. And what that converges on as delta x approaches 0 is what we know as the probability density function. So that's what this function here is. It's if delta x gets smaller and smaller and smaller and smaller and smaller, what does the probability density converge on at that point x, basically? Okay, so roughly, if we want to know what the probability of being in a little interval x to x plus delta x here at this point x, then what we can do, if delta x is very small, then we can assume that the probability density is roughly the same on all of this interval. So if we want to know what the probability of that entire rod or interval is, then all we need to do is take the density of the rod, which we can assume, if delta x is small enough, we can assume it's uniform on that rod. Of course it's not really, but we can assume it is if delta x is very small. And basically all we need to do is take the density and times by delta x. So that will be roughly the probability that you're within that rod, providing x to x plus delta x is very small. So that's just a quick reminder of what a probability density function is. Right, so what this means is that we have mapped our abstract probability space onto onto the real numbers, and we now have what we want to know is what's the probability that you're within a certain interval. Well, we've got this function which we can use, this probability density function, to tell you what the probability that you're within a certain interval is. And how that corresponds to your original abstract probability space is that the probability that you're within this interval x to x plus delta x is going to be the same as the probability of the event, basically an event, remember, is a set of outcomes in this probability space. And this event E is going to be the event consisting of all outcomes, so all outcomes such that the outcome is mapped onto that interval x to x plus delta x. So if I take the image of the point s in this function big X, then basically it's going to be mapped into that interval. So basically this event is the set of is basically the inverse image of this interval. It's all the points which are mapped into that interval by the function big X. Right, okay, so there's the setup for this problem. We've got our random variable now. Now what we're going to do is define another random variable, which is a function of this random variable. So if I move down a bit, and we'll just quickly redraw that picture out. So here is our abstract probability space with its outcomes in. here is our random variable big X, which maps you onto the real line here. And now we're going to create another random variable by taking a function of this. So this maps every outcome onto a real number. What we're now going to do is basically take the function x squared. So we're going to take all these real numbers and we're going to square them. And the composition of these two maps is the random variable we are going to call the random variable y, basically. So it will take, y is going to take an outcome, and what's it going to map it onto? Well, it's going to map it onto what x maps it onto, squared. Okay, so let's say x maps you onto -5, then y is going to map you onto -5 squared, which is 25. So all the outcomes which are mapped onto -5 are also going to be mapped onto the same thing as all the outcomes that are mapped onto 5. So this one is slightly less specific than the random variable x. So this is going to map you onto strictly non-negative real numbers. So I'll put in the interval 0 to plus infinity there. Right, and what we would like to know is, well, firstly, this random variable is clearly very dependent on this one. So if you know what your value of x is, you instantly know what your value of y is. So they're not independent by any stretch of the imagination. And you can see that quite simply because if you plot on R2 the points which are actually allowed in R2, if you were to think of creating a joint random variable x and y, then not all the points of R2 would be allowed, basically. Only the points that lie on this graph would be allowed, basically, because if you the instant you know your x value, your y value is instantly set, basically. So they are not independent whatsoever. By any stretch of the imagination are they independent. So they're not independent. Okay, so what we want to consider is two things, and we'll do this in the next video. Firstly, what is the expected value of y given that we know the value of x? Well, that shouldn't be too difficult, because if we know the value of x, then we instantly know the value of y. So that should be very easy. And then we're also going to look at the expected value of the random variable x, given that we know the value of the random variable y. And that one's a little bit more subtle. Right, so see you in the next video.